Contact light. Okay, engine stop. APA at a detent. Mode control both auto, descent engine command override off. Engine arm off. 13 is in.
We copy you down, Eagle.
Houston, Tranquility Base here. The Eagle has landed.
Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
Although the surface appears to be very, very fine-grained as you get close to it. It's almost like a powder. Ground mass is very fine. I'm going to step off the land now. That's one small step for man, one giant leap for mankind.
Before Neil Armstrong could take that first step onto the moon's surface, a lot of work had to be done. Among the numerous jobs performed was a survey of the moon to see if it was safe for men to venture there. Would conditions require special equipment and procedures? Such important questions had to be answered before the manned expeditions were begun. This is Larry Ross, Director of Space Programs at NASA's Lewis Research Center in Cleveland, Ohio. And I'm the host of this 5th program, Assignment, Shoot for the Moon, in a series of 13 programs called Journey Through the Solar System. Now let's see excerpts from a NASA film which describes the Ranger and Surveyor unmanned missions to the Moon. These spacecraft were launched by the Lewis-managed Atlas Agena and Atlas Centaur.
The assignment was specific. Get photographs of the surface of the moon that are good enough to determine whether or not it's safe for a man to land there. But appearances can be deceiving. Just as deceiving as trying to get a good picture of, well, a candy apple. Doesn't seem to be too much of a problem. Just set it up, light it, and snap the picture. Easy, quick, simple. But it can be tough. As the technology of man in space was developing, it became more and more apparent that our knowledge of the moon's surface as a possible landing site was not sufficient. To land man safely on the moon and get him safely off again, we had to know whether we could set up a precise enough trajectory to reach the moon. Could we design and build a spacecraft to land gently on the moon? Among all those lunar craters, could we find a place clear and level enough for a safe landing site? To make it possible for a man to land in the Apollo zone on the moon, better pictures were needed than those taken through Earth's best telescopes. In fact, better pictures might do more than find a landing site for Apollo. Scientists hoped they might resolve questions unanswered in the 300 years since Copernicus prompted Galileo to study the moon. What were the lunar craters Galileo observed? Pits dug by objects hurled from space, or the scars of old volcanoes? Telescopic photographs, far from answering these questions, scarcely reveal features on the moon as big as the meteor crater in Arizona, almost a mile across and several hundred feet deep. Ranger was designed simply to hit the moon. Before it crashed into its lunar impact point, it would send back to Earth close-up TV pictures of a portion of the moon's surface. The first successful Ranger reached a small lunar sea, since renamed Mare Cognitum, the sea that has become known.
Mark, it is 1 minute to impact. All cameras are functioning.
As soon as the cameras were turned on, the pictures were transmitted to the tracking station at Goldstone, California. From here, they were retransmitted to the Jet Propulsion Laboratory in nearby Pasadena. Here in the Spaceflight Operations Facility, great excitement prevailed as Ranger neared the moon and its pictures came alive on the TV monitor. At last, scientists could turn to close-up pictures like these.
20 seconds to impact. All video good. Signal normal. Stand by for impact. 10 seconds to impact. Video still good. Excellent signal strength. 3, 2, 1. Impact. Impact has occurred.
Prints of each picture were made for immediate study by scientists and engineers. On the theory that all lunar seas were flat and would offer the best landing sites, Ranger examined the surface of 2 such areas. Surprising to some scientists, the photographs at first showed little evidence of any volcanic activity on the moon. No boulders, no rubble, no crevasses, no dust. Pictures of craters covering craters suggested that the surface of the moon was long ago dug into and loosened by repeated impacts. In Ranger 8 photographs, the first signs of volcanic activity on the moon seemed to appear. The lunar landscape Ranger's TV cameras explored was bleak. A flat surface studded with craters. Some are miles across, others no bigger than a washtub. All were probably formed billions of years ago. The last target area was the floor of the Alphonsus crater, chosen because it was not a lunar sea. There was a lot of interest in the dark, smaller craters within Alphonsus, which might explain more about the forming of the lunar surface. On the Alphonsus floor, new signs of variety on the moon's surface began to appear. Craters caused by volcanoes, long since dead. But the evidence from these photographs raised more questions than the pictures answered. Surveyor, a far more complex spacecraft, was designed to make a soft landing on the moon. But once safely down, it would also send back TV pictures of a possible Apollo landing site. The first Surveyor worked perfectly, made its planned soft landing, and sent back more than 11,000 pictures of a small area in the ocean of storms. Surveyor's moon was dark and relatively smooth, but still studded with craters and littered with rocks. Its pictures made it clear that where it landed, there is little loose dust on the surface. But neither is this surface hard. It seems to behave much like earthly soil, and will certainly support the weight of a manned landing craft. It supported Surveyor's weight and offered a glimpse beneath the moon's surface, where the shock absorber sank slightly into the material on which it came to rest. After transmitting the first batch of pictures and surviving the dry heat of a lunar noon, Surveyor slept. It slept through the 14-day-long lunar night as temperatures plunged 500 degrees. Then it came awake on command to continue its examination of the moon. Surveyor took the first color pictures of the moon, showing a blue-gray surface in contrast to the small color wheel attached to one of Surveyor's feet. In some ways, Surveyor's moon seemed more hostile than we thought it might be. Some feared that rocks littering even the smooth plains might present a landing hazard to any manned spacecraft. Lunar Orbiter presented a set of problems different from Ranger or Surveyor. It was designed to circle the moon with a pair of cameras to photograph large areas of the Apollo landing zone and give good close-up pictures of many possible landing sites. Somebody called it the flying drugstore because it develops its own film. The spacecraft also carries an electronic readout system to scan its photographs and send them back to Earth. Lunar Orbiter was an impressive advance in lunar photography. Here was a first close look at large pieces of the moon. 16,000 square miles of the Apollo landing zone, with a resolution 100 times better than Earth-based views. For the manned lunar landing, scientists hope to find a string of sites in groups of 3. Each group a series of 5-mile-wide ovals strung out in a straight line. Each site would have to be crater-free, have no large boulders, and no surface slopes steeper than 7 degrees. Of all the areas photographed by the lunar orbiters, only a few were expected to prove smooth and level enough to meet all the Apollo landing requirements. The spacecraft photographed several suitable areas. Working with the photographs, scientists observed that the smoothest terrain appears to be the darkest. Using degrees of brightness as a yardstick has made it possible to measure the roughness of the moon's surface. Really smooth areas are hard to find. Orbiter missions have resulted in the selection of 8 possible Apollo landing sites. The most promising seems to be a broad plain on the southeastern part of the Sea of Tranquility, just east of the crater Maskelyne D. Its surface is flat. There are no deep craters, few boulders. The other 7 sites stretch along the equator from the Sea of Tranquility to the Ocean of Storms. There was now sufficient data to pinpoint Apollo landing sites for the first mission. In terrain like this, the first lunar landing craft will touch down and man descend to take his first exploratory steps on the moon. Orbiter also photographed the far side of the moon and found it to be even more heavily cratered than the face. These were bonus shots made because the cameras had to be in continual operation until all the film was exposed. The first high-quality pictures taken of this area, they covered 80% of the moon's hidden face. One of Orbiter 2's bonus pictures was a shot of the crater made by Ranger 8 when it impacted the moon. The freshness of the crater was determined by measuring the brightness of the volcanic rock around the crater. Originally concentrated and dark in appearance, the material was now powdered and brightened by the force of the Ranger collision. Lunar Orbiter not only provided outstanding photographs of the moon, it also helped improve our earthbound measurements of the moon's shape and its gravitational field. Micrometeoroid sensors on board discovered that a spacecraft orbiting the moon has no more chance of being hit than one in orbit around Earth. Measuring radiation, Lunar Orbiter 1 experienced 2 solar flares after completing its photography. Flares that would have spoiled its pictures had they occurred earlier. Lunar Orbiter 3 photographed this great 400-mile-long fault, half as deep as the Grand Canyon, and on another part of the moon, a mountain towering 6,500 feet from the floor of a crater. Other orbiter photographs reveal many craters filled with what is apparently volcanic debris. Here is a wealth of material for continued study by geologists and other scientists. For example, the crater Copernicus is one of the most prominent features on the moon. Until not long ago, this photograph, taken through the 120-inch reflecting telescope at the Lick Observatory in California, was the best available. This is Copernicus as seen by Lunar Orbiter 2. 60 miles wide, 2 miles deep, the crater dominates the face of the moon. Thoth, the keyhole-shaped crater in the foreground, is about 13 miles across and nearly a mile deep. Thoth is 33 miles from Copernicus. Much of this distance is covered with debris blasted from Copernicus by the impact of a giant meteorite billions of years ago. Rounding the back shoulder of the moon, one orbiter got an exceptional shot, the first photograph of Earth seen from outer space. From afar, Earth seems shrouded in clouds, much as Venus has always looked. To scientists, this photograph suggests that Venus may not be hidden beneath a perpetual cloud cover. A TV camera close enough to photograph Venus may find holes through which to see this planet with greater clarity. Who knows what a closer look at the evening star will bring? What answers may be found? Or what new questions man may have to ask about the nature of the universe? Other surveyors have touched down near the Landsberg crater in the ocean of storms, and in the Sea of Tranquility, pressing their unmistakable footprints into the lunar surface. Like their predecessor, these surveyors took a good look at themselves and then turned their television cameras on the lunar countryside. One of the most unusual features of Surveyor 3 was its surface sampler. A 5-foot-long arm with a hand-sized scoop. This device was designed to dig into the soil to determine bearing strength and other characteristics. It dug several trenches in the lunar crust. It dumped samples of lunar material on its footpad, allowing close examination of the freshly disturbed soil. In other tests, the scoop was deliberately dropped on the surface, and pictures taken of the resulting dents and cracks. Another surveyor experiment used this alpha scattering device to determine the chemical composition of the lunar soil. At one point, surveyors' cameras interrupted their look at the moon to record this event, an eclipse of the sun by the Earth. The most important scientific conclusion drawn so far from all these photographs is that the moon's ancient surface is still slowly undergoing change. This has been caused mainly by the jarring impact of objects hitting the moon. But whatever the cause, the moon is not, as we thought, a perfectly preserved relic of the geologic past. Lunar Orbiter has extended the mapping of the moon to the far side so that features there could be accurately located, and it also surveyed many important scientific sites. These pictures of the moon's polar areas disclosed striking new details. This is Oriental Basin on the extreme western edge of the moon's disk, and stretching 600 miles in diameter. The mountains surrounding the basin are among the most massive on the moon, rising some 20,000 feet above the surface. Other areas of interest to scientists have been explored. What are the changing red spots that have been seen in Aristarchus? What makes the crater's walls so bright? What kind of erosion created the river-like channel in the Alpine Valley? Was it volcanic? Or was it, as some conjecture, the result of water on the moon's surface eons ago? What is the explanation of Cobra Head? How was it formed? Why are there certain color differences in this region? Near the Harbinger Mountains lie a number of curious craters with sinuous channels extending from them. Scientists will try to deduce what could have happened on the moon's surface to account for them. Because of the astonishing detail of pictures like these, the yield of information is great. For example, this rock is 75 feet across. From the picture, it is possible to tell that it rolled downhill some 900 feet, scraping away the lunar topsoil. This rock is only 15 feet across, but it too left a trail that can be clearly seen. Oblique photos of the Copernicus crater would seem to exclude it as a suitable landing site for a manned spacecraft. But a look at other Copernicus photos taken from a nearly vertical perspective reveals several promising possibilities, particularly here in the northwest area. And surprisingly enough, these lunar photo missions have shown scientists views of Earth no man had ever seen before. This is the first photograph of the nearly full planet from 215,000 miles away. It will provide additional information on the amount of sunlight reflected by Earth. Lunar Orbiter has successfully surveyed 99% of the moon's front face and significantly increased high-resolution coverage of the far side. These pictures are likely to be the source of lunar surface information for many years and should contribute to a fuller understanding of the moon. If many other questions are still in doubt, some of the answers may already be in our hands. Examination of these photographs is not complete, and already they've produced miles of data tapes to be processed. And additional information is being returned so rapidly that it will take years to evaluate it all.
When the TV cameras on Ranger 7, 8, and 9 in 1964 and 1965 took close-up pictures of the moon just before impact, astronomers were very pleased. Ranger 7 had confirmed that there were lunar regions topographically acceptable as landing places for the manned Apollo spacecraft. The resolution of Ranger 8 was about 10 times better than that of the best Earth-based telescope's resolution. Ranger 9's last photograph was taken a quarter second before impact. The picture showed an area 200 feet by 240 feet. After the Surveyor 1 spacecraft soft-landed on the moon in June 1966, a heavily pockmarked surface was revealed. Craters of all sizes and rocks were examined with a Surveyor camera. The soft landings on the moon by Soviet and U.S. spacecraft confirmed that the lunar surface would support a manned landing craft. Set to rest were theories that the moon's surface was like cotton candy or whiskers, or was a very deep, soft dust. The stage was now set for men to go to the moon for the first time, a truly momentous occasion in the history of all humankind. Men were to bring back samples of lunar material for detailed analysis here on Earth. These lunar rocks and soil were to tell us if the moon were made of Earth-like material, and analysis would tell us their age. A new science was to grow out of this exploration of the solar system, comparative planetology. We were destined to learn more about other worlds and to compare them to Earth. We could then deduce more about Earth and its destiny. Our next episode, the 6th in the series of 13, is called The Moon and Us. During that program, we will see highlights of many of the manned expeditions to the moon. It was an exciting time when the peoples of the Earth stopped their daily pursuits to watch this live, televised history in the making. The impact was felt by millions of us as Armstrong stepped onto the moon's surface. And all shared the excitement of discovery and exploration, emotions until then the exclusive property of only a few in history. Until our next show, this is Larry Ross at NASA's Lewis Research Center in Cleveland, Ohio, saying goodbye. The moon had been photographed by a variety of spacecraft. Machines had landed on the moon to observe it. Now it was time for man to make ready to go there. I'm Larry Ross, Director of Space Programs at NASA's Lewis Research Center in Cleveland, Ohio, and I'm your host for the 6th episode of our 13 programs called Journey Through the Solar System. Now let's see parts of several NASA films which document both the science and the excitement of this Apollo lunar program.
The moon is a different thing to each one of us. I know my own impression is that it's a vast, lonely, forbidding type existence or expanse of nothing. and clouds of pumice stone. And it certainly would not appear to be a very inviting place to live or work.
Scientific sextant observations made on Apollo 8 were a practical, potentially vital gathering of scientific data. Taking the longer view of the scientific value of the mission, comment was made by Dr. Leo Goldberg, astronomer.
I believe the Apollo 8 mission will ultimately prove to be of enormous scientific importance as a vital step that had to be taken before men actually land on the moon. Once they do, the exploration of the moon is bound to give us crucial information on how the moon and other bodies in the solar system were formed.
Doctor, a second, I hope. Roger. That's mapping. We're there. Got 2 crates. Roger. You saw the docket, Charlie. Any master alarm, everything looks snug.
Apollo 10 had a rugged flight plan. It combined the features of the 9 flights before it and was a full dress rehearsal for the infinitely complicated lunar landing to follow. Astronauts Stafford, Young, and Cernan became the second group of 3 to see this sight. And they were the first with the potential to see it from a point 60 miles closer than it appears in this scene. It was a prime objective of Apollo 10 to duplicate the Apollo 11 flight plan in every way. The timing, spacecraft performance, the performance of men and equipment on Earth. As they disappeared behind the moon for the 11th time, they were still together. When they next appeared, they were 50 feet apart, flying formation. John Young radioed his companions below. "You'll never know how big this thing gets when there ain't nobody in here but one guy." And they answered, "You'll never know how small it looks when you're as far as we are." Here in the lunar environment, as Apollo 9 had done in Earth's environment, the crew was able to check out the lunar module's landing radar, navigation, and guidance systems. They were also proving out the descent rocket, an engine which can be throttled like an ordinary car. The reflection in the window comes from the astronaut's sleeves as he took the pictures.
Down among us, Charlie.
Roger, you're weaving your way up the freeway.
The waterless Sea of Tranquility was their target, and the descent orbit swept them in lower and lower for the first pass over landing site number 2. This is a preview of what the crew of the Apollo 11 will see when they head in for lunar landing.
Down 2.5. Forward. Forward. That's 40 feet down 2.5. Picking up some dust. 4 forward. 4 forward. Drifting to the right a little. That's okay. Contact light. Okay, engine stop.
We copy you down, Eagle.
Tranquility Base here. The Eagle has landed.
Through the window of the Eagle, Armstrong and Aldrin see what no human eyes have ever seen before. Their spacecraft casts a long shadow across the undisturbed dust of centuries. The first footsteps on this strange new world must be taken cautiously. The moon has only 1/6 the gravity of Earth. The nature of its surface was still unknown.
I'm going to step off the limb now. That's one small step for man, one Giant leap for mankind.
In addition to collecting rock and soil samples, the explorers leave behind a seismometer. This highly sensitive device would send back valuable information on external meteoroid impacts, as well as internal lunar movements. A 100 prism laser reflector would help man to measure the exact distance from Earth to Moon to an accuracy of 6 inches. These were the first of many experiments which will be taken to the Moon to provide man continuing and increasing knowledge about the Moon and the vastness of space beyond.
Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engines running. Commit. Liftoff.
Apollo 12 lifted off in the driving rain.
Pete Conrad reports that your program is in. Tower clear.
Conrad climbed out first.
Okay, I'm at the porch. Hey, I'll tell you what we're parked next to. What? We're about 25 feet in front of the surveyor crater.
They prepared an experiments package to be left on the Moon, an automated scientific station called ALSEP that would send information to Earth for a year, powered by a nuclear electric generator. ALSEP, an acronym for Apollo Lunar Surface Experiments Package. Piece by piece, they assembled the station.
Okay. Can I get the solar wind deployed here?
The solar wind experiment, to measure atomic particles thrown off by the sun as they strike the Moon. A device to measure the Moon's tenuous atmosphere. A magnetometer to measure the lunar magnetic field, which would later be found to be 10 to 20 times stronger than many scientists had expected. A seismometer to measure physical properties of the crust and interior. And the data station to collect the experimental measurements and transmit them to Earth. With ALSEP deployed, Conrad and Bean began collecting geological samples.
Oh, gal, there's just a rock. Look at that. Son of a gun. They gotta have that. 15 at 1. -1. -1. 6% fuel. 10 feet, -1. 8 feet, -1. Contact. Bam. Okay, Houston, the Falcon is on the plane at Hadley. Roger, roger, Falcon. No denying that, we had contact. Houston, the Hadley base here. Tell those geologists in the back room to get ready, because we've really got something for them.
Scott and Irwin were located on an undulating plain situated between the Apennines and Hadley Rill, an area selected by the scientists as being one of the most geologically significant sites on the Moon. They would observe the layering of the lunar terrain, most clearly seen in the formation 14 miles to the south, called Silver Spur. This layering, later to be observed in the mountains and the Rill, gives scientists a direct look at the structure of the Moon and a deeper insight as to the significance of the collected samples. 60 miles above the Moon, Al Warden orbited in the command module Endeavour, operating experiments, his observations adding to the wealth of scientific data already accumulated.
Okay, I'm looking right down on Letro now, and a very interesting thing. It looks like a whole field of small cinder cones down here.
The detection of cinder cones, clearly of volcanic origin, helped solve another element of the controversy about how much of the moon was formed by volcanoes and how much by meteoroid impact. Worden was operating a series of experiments in the scientific instrument module. These included a mapping camera to shoot lunar features and simultaneously the star field for accurate location of these features, a panoramic camera, a laser altimeter for accurate topographical mapping, and a series of experiments to analyze the chemical makeup of the lunar crust. In the estimation of a number of scientists, this orbital research station would provide the most important information collected during the mission.
Look at that. Almost see twinning in there. Guess what we just found? I think we found what we came for. Crystal and rock, huh? Yes, sir. You better believe it.
To the untrained eye, it looked like just another rock. But its large crystals, formed in pairs called twinning, showed it to be a section of primal lunar crust, formed during the earliest history of the solar system.
Yes, it is. If we could just get our shoulder under that.
Their first stop was at the drill they had left during the second EVA. This core tube was the deepest sample ever collected from the moon, perhaps the deepest we would ever get, 8.5 feet beneath the surface, cutting through 58 distinct layers. This would not only tell us more about the lunar structure, but contained in this soil were traces of particles emitted by the sun billions of years ago, which would give us a clue to the early years of the solar system.
Young set up an ultraviolet camera to provide the first astronomical observations from the moon. He took pictures of the Earth's upper atmosphere and magnetosphere and their interaction with the solar wind. He also photographed the interstellar gas present throughout space and the ultraviolet halos that appear around galaxies. Young placed a series of sensors in the soil, then fired explosive charges, mapping the lunar subsurface much as geologists on Earth use explosives to search for oil.
4, 3, 2, 1, fire.
Young used a portable instrument to measure the local magnetic field. He would later record the most intense magnetic field ever found on the moon, far higher than scientists ever suspected. With Duke acting as photographer and Young as driver, they put the rover through a full test.
Man, you are really bouncing it.
Then, one of the most spectacular discoveries of the mission.
Look at the size of that biggie. It is a biggie, isn't it? It may be further away than we think. No, it's not very far. It was just right beyond you. And we better press on for the big boulder? Okay, we're headed that way. You get the tongs, John? Yep. I'll carry the rake.
That big black dot. Fantastic. Right here.
If we could see to the bottom, we could say for sure if this big black rock is right out of the bottom. But my guess from the old photographs is it probably is. Okay, that sounds like a good guess. Pottery, it's obviously very cohesive because the bottom of the core is not smooth, it's very jaggedy and fragmental-like.
They would sample several locations on this EVA, but none would cause more excitement than the find at the crater called Shorty.
Oh, hey! There is orange soil. Well, don't move it till I see it. It's all over. Orange! Don't move it till I see it. I've stirred it up with my feet. Hey, it is! I can see it from here. It's orange.
That's the volcanic mix.
Somebody unplugged over.
Fantastic, sports fans. It's trench time. Jack, that is really orange.
I think it's the most exciting we have come across since the beginning of the Apollo program. I believe that it's going to be the most rewarding of all the finds on Apollo.
99, proceeded, 3, 2, 1, ignition. Right away, Houston. Bets are good.
17 was the last Apollo mission to the moon. Now, what did we learn after the data, rocks, lunar soil, and photographs were returned? A NASA film called The Moon, an Emerging Planet begins to tell us the results.
In many respects, our moon is one of the strangest bodies in the entire solar system. Of all the terrestrial or four innermost planets, only Earth has such a large moon. Compared with the terrestrial planets, the moon's density is much lower than we might have expected. Compared with Earth, the chemistry is much different. Before the Apollo program, three major theories arose to dominate scientists' thinking about how the moon was formed. One suggests that the moon split off from the Earth and was flung into orbit around our planet. A second theory suggests that the moon originated as a twin planet, perhaps from materials left over from the formation of the Earth. The third theory holds that the moon was captured by the Earth's gravitational attraction, having been formed somewhere else in the solar system. There are problems with each theory. It has been suggested that it would be easier to explain our moon's absence than its presence. Nevertheless, from the data returned by the remarkable Apollo flights, as well as unmanned missions, we have learned a great deal about the moon's evolution and early history. It has become, in a sense, an emerging planet. Unless it split off from another planet, it must have originated as a tiny body, perhaps one something like Phobos, one of the moons of the planet Mars. And it grew by a process of accretion, an accumulation of objects drawn together, often in massive collisions by gravitational attraction. These objects ranged from microscopic dust particles to asteroids. By 4.6 billion years ago, the moon had reached its present dimensions. During the last 10 to 100,000 years of this primeval bombardment, the collisions may have generated so much heat that the entire outer shell of the moon may have turned into a seething global ocean of molten silicate materials. Once bombardment slowed, the liquid shell began to cool, solidifying over a period of tens of millions of years. Crystals rich in calcium and aluminum formed. They rose to the surface and produced a mush which eventually solidified to become the dominant light-colored material we call the highlands. Simultaneously, dense crystals rich in magnesium and iron formed and sank to the bottom, becoming a distinct dense layer. There was now a lunar crust, a product of millions of years of crystallization. 100 to 300 million years later, radioactive heating became extensive enough to melt materials in the shell just beneath the crust. The melting produced pockets of liquid, giving rise to volcanic eruptions 4.4 to 4.3 billion years ago. At the same time, it seems that globules of molten material rich in metallic iron may have accumulated, and they settled down into the center to form a core. If 2 to 3% of the original moon consisted of metallic iron, the core could have a radius about 1/5 that of the whole globe. Such a differentiated moon, with a crust, a mantle, and a core, came as quite a surprise to many scientists who had expected the moon to be homogeneous, with materials distributed more or less evenly throughout. A molten core rich in iron could have functioned as a huge dynamo, much like the Earth's core, and produced a magnetic field. This would explain the magnetic properties of many of the lunar rocks which have been returned by Apollo crews. According to theoretical studies, the moon and Earth serve as very efficient celestial vacuum cleaners. And within less than 100 million years after their formation, they should have swept up most objects in their vicinity. Surprisingly, 600 million years after the formation, or 1/2 billion years later than we would have expected, huge objects were still impacting on the moon, helping produce the rugged surface. Some of them were as large as the state of Rhode Island. The final ones blasted out the great circular basins we see on the moon's face today. One of the final large impacts, which we call the Imbrium event, produced the circular feature which now serves as the right eye of the man in the moon. By the time of the Imbrium impact, the exterior of the moon had cooled to depths well below the crust. The interior, by contrast, began to warm up, a result of natural radioactivity. At a depth of 150 miles, perhaps 300 miles, a zone began to melt, producing liquid silicate material that accumulated in pockets. The liquids then found their way to the surface, sometimes following fractures in the crust, sometimes forcing a passage through solid layers. One volcanic flow after another filled in the great basins produced by the large meteoroid impacts, and became what Galileo Galilei called the lunar maria, or seas. After some 1.5 billion years, major volcanic activity on the moon had come to an end. Except for a last gasp of volcanic activity originating deep in the lunar interior, rare meteoroid impacts, such as the one which produced the crater Copernicus, and occasional small moonquakes. The peace of the moon has been largely undisturbed for 3,000 million years. We have thus learned a great deal about those early events and processes which produced the moon. And it seems likely that similar events and processes were at work on our own planet. The Earth's early geologic records, however, have been largely obscured by extensive volcanic activity, faulting, folding, erosion, sedimentation, and other geologic processes. What few of the ancient records we do still have on Earth are being illuminated by our lunar studies. It is clear that the moon had a violent and dynamic early history, and that major geologic activity had come to an end by 3 billion years ago. Unlike the moon, the Earth did not die. Indeed, its geologic activity increased. By 500 million years ago, hard-shelled animals had appeared on Earth, and they left their fossils in rocks we find today. It was only about 200 million years ago that the present continent split and began to drift apart, a process which continues to this day. In essence, it is possible that the Earth and Moon had quite similar early histories. In studying the Moon, we are taking our first close-up look through what has been called a window to the history of our solar system.
The moon has shown no evidence of life. Still, we wondered if there was life elsewhere than Earth in our solar system. The next logical candidate for the search was Mars, fourth planet from the Sun. During our next episode, we will examine Mars from space. This is Larry Ross saying goodbye from NASA's Lewis Research Center in Cleveland, Ohio.